Thank you so much. Thank you to the organizers for the invitation. So I originally, I think, was invited to speak about my one and only paper on social dynamics, which I think makes for a good 10 to 15-minute talk. So being aware of the schedule, I changed the topic slightly, and so I'm going to give a bit more context about the mathematics of intelligence as I see it. And so I'm going to talk about emergence of intelligence, and we're going to go from neurons all the way to social dynamics. And so I'm currently the head of research at the Utah AI Policy Office. I started that job 2 months ago. Up until then, I was a postdoc at Dartmouth College in the Department of Mathematics. So, and that recent change also motivates some of the things that I want to talk about. I want to talk about intelligence, specifically artificial intelligence, because that is now the bread and butter of my job. I want to talk a bit about complex systems research. I'm going to use some examples from my own research trajectory, namely, they're going to come up in a bit. And then I want to talk a bit about how they're connected. And I decided to include this in this talk specifically for people at a younger career stage who are maybe still in the process of figuring out where to go next, because I feel that there are some lessons that I learned very recently in doing a career change myself. And so, interesting. Okay, so I'm going to start by talking about what I think intelligence is. And then in terms of moving from neurons to people, we're going to start with a little bit of research that I did on correlational patterns that arise from neural dynamics. And then we're going to move on to a mathematical model of plant behavior in social dynamics. And then finally, I want to talk about where I see connections between collective dynamics and artificial intelligence. And so let's start with what is intelligence? And now there's, 30, 40 people in this room. So I think we'll have about 50 different answers to these questions in this room alone. I'm just going to reuse some of the slides that I used in my mathematics and AI course that I taught at Dartmouth College. So this is lecture 1. Welcome to Dartmouth College, the birthplace of artificial intelligence. Here is where the word artificial intelligence was coined by John McCarthy a long while ago, who later became a bit more cynical about it and said, as soon as it works, nobody calls it AI anymore. So if I go onto Merriam-Webster to find out what intelligence is, I get the following definitions. And so some of the words that come out here that I want to highlight are reason, information, and comprehension. So reason, if we're looking for an artificial system that can reason, and I want to be a bit cocky about it, I could say this system can reason, right? Because you have an input, sunlight coming in at an angle, and there's reasoning built into the architecture of the system that's going to tell us what time it is. Now, most people would not consider this an artificially intelligent system, so we want to implement some other aspects into that system too. Now, if we look at information, what are systems that can store information? I would argue this system can store information. Now, maybe you say, okay, well, this system can store 7 numbers. Maybe I want to store a bit more than that. And so this you might consider not an intelligent system, but would you consider this an intelligent system? Because it has a lot of information stored in it, right? So somehow that seems to still not be enough. And then moving on to comprehension, which is my least favorite part about this definition, because it's the least tangible, seems to be that the goalpost for comprehension seems to be constantly moving, of saying, well, machines don't understand because they can't do that one specific thing that people would do with information. And as soon as they can, we're going to say, well, they're still not comprehending because they can't do this other thing. There's a lot of people who try to get at the problem of comprehension in very intelligent ways, in part using integrated information theory that we heard about yesterday, for example, but this is not something that I want to talk about today. So One thing that comes out for me in terms of looking at these aspects of this definition and the ways that we can play around and say, well, is this intelligent, is this intelligent, kind of fulfills the definition, but doesn't really feel intelligent, is that something that a lot of people, just not in terms of definition, but in terms of vibes, might feel is related to intelligence is actually the process of emergence. We're looking at a system where it's not evident necessarily from just looking at it how exactly the reasoning evolves, how exactly the information is stored in there, but somehow, by some set of rules, there's some reasoning and some information retrieval that the system can achieve. And so that motivates, I think, my angle in terms of research in the field of intelligence, most broadly speaking. So any system that can somehow respond in a intelligent, maybe self-serving way to external stimuli, I think if we're generous, we can think of that as an intelligent system. And a lot of these systems, we like to think about them as systems that are composed of smaller entities. So in collective dynamics, we have that. In network science, we have that. Systems composed of nodes and edges. And the systems that I'm mostly interested in are networks that have some relationship to dynamical systems. So this can either be networks that change structurally over time, so looking at temporal networks, networks where connections indicate certain collaborative events and may occur and then disappear again, but also networks that have dynamics living on them. So you could think about a network of roads or streets and whatnot, and you have traffic moving on it. So most of my mathematical research was around using some either discrete or continuous dynamical systems to describe these types of settings. And one piece of research that I want to talk about today was motivated by the study of neural dynamics on networks. So think about neurons in a brain. They don't have to be neurons. In fact, it was mostly motivated by understanding patterns in calcium imaging, where typically the one pixel in an image does not necessarily correspond to a single neuron, but that's a different story with lots of data science challenges related to it. And so the thing that I was interested in was when we see correlation patterns arising through dynamics on a network, how are those related to the network structure? And I wanted to take, a bottom-up approach to that, starting out with network motifs. So I think motifs came up yesterday in Bernard's talk about baseball players and the kind of motifs of passing balls along to understand how a baseball game works. In a somewhat more conventional setting where we have a static graph, a lot of times when people talk about motifs, they talk about small subgraphs. So here we have an example of a directed graph. Very simple. We have 6 nodes in this graph, and I'm now going to look for motifs in this one. So for example, I'm going to say the motif that I'm interested in is this smaller directed graph over here. So what I'm going to do is I'm going to go into this graph, and I'm going to look for subgraphs that are isomorphic to this, right? So I'm going to look for subgraphs that look just the same. And I'm going to count them, and I'm going to find, in this case, the following 5 occurrences of that. So this directed to path over here, we have one subgraph that looks exactly like that, is given by these dark purple edges over here. Then we have one that is given by these orange edges over here, and so on and so forth. So when you think about motifs and networks, what you're thinking of is basically you have a small blueprint, and then you go into your actual system, and you count how many occurrences of that blueprint you find in your system. This is for static graphs, and I was interested to look at this in the context of having dynamics on networks. Now, having stared at that problem for a long time, the way that my PhD advisor and I thought would be best to try to characterize this was to think of motifs instead of small subgraphs of small processes that can happen on your system. And these processes are just going to be entities that move along your network. So here, I'm taking an even simpler network to start with. We have two edges over here, two nodes in a directed network. And now I'm going to ask, what are possible ways that an object could move on the structure? Now, the simplest thing that can happen if anything moves at all is you start somewhere, you go another place. So you're traversing one edge, you have one entity doing that, and we're going to denote that microprocess by this graph with that curved edge over here, one indicating that it takes exactly one edge to traverse to get from your start point to your destination. There's other things that you could do on this graph too. So you could start, for example, at one node, take 2 steps and arrive back at the point where you started out. We're going to denote this by this little graphlet over here. And there's other processes that you can think about as well. For more technical reasons, we're making a distinction of having basically this being a special case of the case of moving 2 steps in any direction, and only in that special case you arrive back at your starting point. You could think about 2 entities starting at different nodes, both moving one edge at a time, and so on and so forth. Now these are the ones in blue. Those are the blueprints that I mentioned on the previous slide. When we look at how often they can occur on that system, we see that, for example, that very simple blueprint of just having one step along one edge. There's 2 ways that you can do this on this network, starting either at node I or node J. And similarly, you can do that for the other microprocesses too. Now, technically, you can go on with this forever because this is a cyclic graph, so you can keep moving and moving and moving. So there's an infinite number of microprocesses that can happen on here. If I just cut one of these edges, this becomes a lot simpler because there's exactly one thing that can suddenly happen on here, and there's exactly one occurrence of that. And then one-to-one mapping is actually something that we explored for the use of causal inference in these types of systems in a paper that I'm not going to talk about today. But I think there's just what I want to allude to is that this is not just kind of intellectually satisfying. There are also some data scientific implications from it. So I was talking about having dynamics on these networks, and being at a math workshop, I figured I at least show you one equation over here. So we're going to have a dynamical system on this network. It's going to be a linear stochastic process where we have some noise term over here. We have some coupling term over here. Coupling is governed by the adjacency matrix of my network and a parameter that tunes the coupling strength. And this is a special case of the Ornstein-Uhlenbeck process, which is a mean reverting process, meaning that you initialize that system somehow. There's going to be some noisy relaxation down to all of the node states eventually being close to 0, kind of bobbing around in that area. A nice thing about the system is that it's really well studied and mathematically tractable. So one thing that we can do is we can look at that steady state around 0 that I just mentioned, and we can look at the covariance matrix at that steady state. So there's going to be a stochastic steady state with a covariance matrix that is fixed over time. And if we look at that, we can get an analytical formulation for that is going to look like this. Those C with a bunch of subscripts, those are just going to be a number that depends on a bunch of parameters of our system. And then we have that second term over here that has powers of the adjacency matrix and the adjacency matrix transposed. Now, if you remember like your first linear algebra or your graph theory class, you might have learned about how when you take powers of the adjacency matrix, those elements of that power are telling you something about how many ways there are to get from node I to node J in your system. If you do the same and you then multiply it with some power of the transpose, what you get is a count of the number of ways that you can start at some unspecified node in that system, and in some number of steps get to node I, and simultaneously in another number of steps get to node J. And those numbers are going to depend on the powers of those A and A transpose terms over here. And so what this gives us is actually one of those microprocesses that I just talked about, right? So this basically is a process where you have two entities starting at some unspecified source node, and one is going to go L steps in one direction, and the other one, so lowercase L steps in one direction, and the other one is going to go, in this case, uppercase minus lowercase L steps in the other direction. So in total, there's a number of uppercase L steps being taken, and lowercase l governs how many steps are taken towards the left and how many steps are taken towards the right. Now that number that depends on our various systems parameters, that is going to tell us how much each of these processes is going to contribute to the covariance at steady state in our system. And this is really cool because it gives us really intuitive results. So here we have the coupling strength, we have the number of nodes in the system, we have the noise strength over here, and we have those parameters uppercase and lowercase l that relate to the microprocess that we're interested in. So this says what we see in terms of covariance at steady state is accumulates from a bunch of microprocesses happening on our network, and they all kind of have this structure. But depending on how many steps are taken in total and how many steps are taken towards the left and to the right, we have different contributions. So some microprocesses are going to be more important than others in terms of contributing and shaping what we get in our covariance structure. Now, to show why that has some really nice intuitive results, let's think about it. So this is me sending a message to two of my friends, right? I could be a person, I could be a neuron. Us in complex systems, we don't really care about that so much. Everything it's just a node somewhere that talks to other nodes. So I'm going to yell at Gulsha, and then I'm going to yell at Govind. And if you're kind of at similar distances away from me, then you're both going to be surprised around the same time. But if you're on the other end of campus, and somehow I could yell as loud for you to hear me over there, there's a noise gonna travel at a certain speed, and so you're going to be excited much earlier than you're going to be excited about hearing me yell at you, if that is exciting to you. So in terms, when we're looking at the correlation between the two states of Govind and Gulsha, what we're going to see is that the correlation between the two is going to be high when the number of steps taken to the left, so the distance between me and Gulsha, is going to be roughly the same than the number of steps, so the distance between me and Govind over here. And this is precisely that yellow corridor that I've highlighted here in this graph, where we have roughly the same number of steps towards the left and towards the right. The other thing that we see is that overall the number of steps that we take, so uppercase L, also governs how strong that correlation between nodes I and J is. If signals have to travel through the system for a long distance, then because we're losing some of the signal-to-noise ratio on every edge, we're seeing a weaker effect than in those cases over here, where we're basically just traveling 1 or 2 steps in total. And this basically is just a graphical illustration of something that you've all heard before, right? Correlation is not causation, right? So when we see that two things are correlated, that can be because either there's a signal going from I to J or from J to I, or it can be because there's some confounding factor that happens to hit those two nodes at roughly the same time. Now we can do the same thing not just for covariance. We can do that too for variance over here, which is really just a cheap result where you say, okay, what happens when nodes I and J are the same thing? What you then see is that variance is governed by the overall noisiness of your dynamics to kind of a zeroth order and then to a first order by motifs like these where you have some other node communicating to that node via different paths. Basically some self-amplification of the signals that node I receives. And then over here we have the same spiel for correlation in systems, where correlation to us just means covariance normalized for variance at each node. This looks like a bit much, but what it actually just is we have a microprocess for covariance connecting nodes I and J, and then we append a bunch of motifs for variance at each of those nodes. And how many we attach, that's really up to us. Any number is valid. Any one of these composite processes is going to have some contribution to correlation in our system. So one caveat of that is that you end up with, yes?
I'm slightly confused by your diagrams where I'm seeing directed edges, but I think this is all coming from an adjacency matrix that doesn't have direction. Is that right?
It does.
Oh, it does.
It does, yeah.
Okay. It's more of a directed graph.
Yeah, so we're assuming a directed graph. It also works on undirected graphs, but a lot of things would simplify, like the ANA transpose would basically just melt to some power of the adjacency matrix. So you could do it, but insights aren't that great. So in the case of correlation, we have a bunch of these parameters now because we need to specify essentially all the numbers of edges that you traverse going along any of these blue arrows over here. So it's kind of hard to explore the full space of possible motifs for correlation, but just looking at like a slice of those, we're going to assume that all of these walks from some source node to either node I or node J are just going to be exactly one step. And the only thing that we're going to vary is how many of these motifs for variance are we going to append to nodes I and J. Now, what we see here is that, again, motifs that have an overall smaller number of steps, so that would put us down here, are the ones that have the strongest contribution to covariance in a system. The other thing that I think is really interesting about this is that we now have positive and negative contributions. So before we had, when we were looking at covariance, everything that was contributing in a positive manner. Now we can have microprocesses that have a negative contribution to correlation. And I'm going to talk a bit more about why I think this too can be intuitive in just 2 slides from now. So I've been talking about a bunch of microprocesses happening on your system. If you're really into dynamical systems, like I am, then this might be really appealing to you. But if you're like a core network scientist who's mostly interested in structure, you say, I'm interested in network motifs in the sense of subgraphs in a larger network. I don't really want to think about these things. Tell me something about how small subgraphs in a network contribute to covariance or correlation in my system. That's what I want to know. And the good thing is we can do this simply by looking at small subgraphs or potential subgraphs of a larger directed network and saying, what are all the microprocesses that could happen on this small subgraph? So we know for this graph there was exactly just one. This graph has a cycle in it, so we have a self-edge over here. This gives us an infinite number of those, but those very large ones are going to have infinitely small contributions. Ultimately, if we're choosing the parameters of a dynamical system such that there is a stable state, all of these sums are going to converge, and what we can do is we simply sum up the contributions of all the possible processes that can happen on such a small subgraph, and then we get a number. That number is going to depend on the parameters in our system, and it's going to tell us about how these potential subgraphs are going to contribute to covariance in our system. Over here we have the subgraphs that are going to contribute to correlation in our system. And here we see that some subgraphs have a positive contribution to both covariance and correlation. Some subgraphs don't have any contribution at all. And that again makes sense. So if you look at this graph over here, there's no connection between the nodes I and j. There's no reason why this should contribute to covariance or correlation between these two nodes. But then over here you have some subgraphs that seem to have a negative contribution to correlation in that system. You don't have a contribution to covariance. And the reason is that the way that we're calculating these numbers, we're essentially looking what is the composite effect of having all of these edges together. So we're subtracting the effect of having one edge already. And we're looking, so this number tells us something about how does having another node pointing at node I change this contribution. So this is what this number tells us. And if we look at it, so this is, J is me again, and I'm again shouting at Gilsha. And now the rest of the room, or at least one other person in this room, is also going to shout at Gilsha really, really loudly. And then we're going to look at how much did Gilsha understand from the information that I tried to convey. And the answer is if there's other people shouting at her at the same time, that's going to become more difficult. So having that extra person shout at node I over here therefore leads to, it is some intuitive explanation of why we see a negative contribution of having this motif over here. So to conclude that first part, I'm surprised that I made it through it with just a single question. I was talking about how we can think about motifs to build up a bottom-up understanding of dynamics on networks. And I talked about some notion that I called microprocesses or process motifs, where instead of looking at small subgraphs, we're now looking at small microprocesses of how entities can move on a network, either one or several entities at the same time. Then I showed that we can use these microprocesses to understand the correlation and covariance patterns that we see in a linear stochastic process on a network at its steady state. Excuse me. And then finally, we looked at how this gives us some insights about how small structures within a network, so small subgraphs, have some contribution to the correlation and covariance structure in our system. And so I was highlighting along the way at several points that I think it's really satisfying to see the intuitive explanations that come alongside with these results. But I also think it's important to highlight the potential here of being able to kind of, from the mathematical model, using only derivation, to arrive at essentially a bottom-up understanding of what the correlation patterns in a network are going to look like. Now, the process is tedious, and you'd be probably, if it's just about speed, it'd be easier for you to just run a simulation and then calculate a covariance and correlation matrix from your simulation results and be done with it. But this process enables you to get results without running any simulation and getting sort of a mechanistic understanding of where these correlation patterns come from. And therefore, if you're looking at an application where, for example, you want to anticipate or you want to design a certain correlation pattern where you have control of the network structure, I think this gives you a nice tool to think about how you want to go about that design process. And I'll come back to that at the very end of my talk. So let's get to the second part, my one and only paper on social dynamics, where a special thanks goes out to the first workshop on women in complex systems. This was a collaboration that came out of that workshop, and as it is with workshops, they're like here, it can be an incredibly stimulating environment. It can also be an environment to try out something that you've never done before, and for me that was trying out modeling social dynamics. And so that's what we did, and we were thinking about how does collective action in groups of people form. So one of the examples, and I apologize if this is too soon for some people in the room, one of the examples that we thought about was political activism. So for example, I have agency, and if I have a front yard, I have agency about what signs I'm going to put up in that yard. I could decide to put up a sign supporting one presidential candidate. I could put up a sign supporting another presidential candidate. I could decide to not put up any sign at all. I could decide to put up 5 signs because I'm really convicted. I could decide to put up a second sign after the first sign gets stolen. All of these are possible decisions that I could take. Now, if you don't want to think about politics, you have collective action forming at other levels as well. So, for example, we have decisions as to whether or not to get vaccinated. We all know that for some people, this is a really contested topic. There's a lot of a mixture out of social pressure in one direction or another, and a lot of signaling as well. So, for example, I remember when I got my first COVID vaccine, and there was like a "I got vaccinated" sticker that you could put on your jacket for that day. So you have in all of these decisions, you have that there might be both some internal attitude towards taking an action or not. I might have some conviction and believe that one of these candidates has better values than the other and therefore should become president. But I then also think about, when I put up that sign, how is that going to affect my interactions with my neighbors? Is that actually going to make a difference? Is it worth the effort that I put in? If we want to get away from topics that are contested in any of these cases, you could also just simply think about health behaviors. So there's a huge body of research about how a lot of healthy lifestyles actually involve group dynamics. So that, for example, if you're struggling with obesity, but all of your family dynamics are centered around having large, unhealthy, long meals, it's going to be really, really difficult to say to an individual, well, you just got to start eating carrots and nothing else anymore because it's socially isolating. So really, for a lot of the health behaviors that essentially decide whether we live healthy lives or not, there's a social component to it that plays a large role. Now, one very subtle example is that you can't really go jogging in your neighborhood without all of your neighbors knowing that you go jogging. So whenever you start jogging, you're signaling something to your neighbors, whether you want it or not. I'm not a jogger. I'd be one of those people sitting resentful in their window and like being mad at my neighbors for making better life choices than me. So what I'm trying to say with all of these examples is that we have some weaker or stronger notions of collective actions, where there's both some internal motivation to do something or internal motivation not to do something, but you have that competing with some sort of perceived social norms that you see in communities. And that is something that we don't often see actually in complex systems modeling of opinion dynamics. So one model that maybe is a bit out of fashion today, but essentially one of the influential ones is the Watts-Strogatz. Did I say Watts-Strogatz? It should be say Watts-Threshold model over here. So here we assume that we have a collective of people. Each person is a node. There's some network structure that limits to what extent you can see the actions of other nodes. And what you're going to do is you're going to adopt whatever the dominant opinion is among your neighbors. So if more than 50% of your neighbors say, I'm for the blue side of the debate, then you're going to switch to blue. And so if we run that system, this is a discrete system, we run it with this initialization over here, we see that we have a bunch of nodes adopting based on them being connected to at least two of these other nodes over here. We can continue running it. Eventually we've reached peak adoption and nothing is going to change after that. And so one criticism that I have of this model is that it basically doesn't give any agency to the actual agents in this system, right? In this setting, we have people forming opinions based only on what they see other people doing. So if we want to change that, if we want to say, well, things like beliefs and intentions matter, we probably need a more complicated mathematical model for that. And so that was what motivated us to look into psychological theory and try to put some of that into a mathematical model for collective opinion formation. And we turned to the theory of planned behavior simply because it's a well-established psychological theory of how people decide to take actions. In that theory, and this is, I put in like math symbols over here, but at its core, this is a qualitative theory which says that when you decide to do something, the things that influence your decision-making process are going to be your internal values, your internal attitude, your perception of social norm. Now, this is important for the network scientists in the room because your perceived social norm can be different from the actual social norm in the system. So if I only see people who put up Harris-Walz sign in their yard, even if there would be a majority of people not doing it, my perception would be that there's a social norms towards doing that. And then there's a third component called perceived behavioral control, which just means that if I feel like my action is either not going to matter at all, like it's not going to make a difference, or there's something keeping me from taking that action in the first place. Say I don't have the money to buy a sign, I don't have a car to go to a place to get a sign, whatever, something like that. If I feel like I can't do it, or if I do it, it doesn't make a difference, I'm perceiving my behavioral control to be zero. And that would mean that I have, it dampens or completely nullifies my behavioral intention. So this looked nice. This almost looks like we can go back to some compositional modeling for the category theorists in the room. I like ODEs, so we put all of that in an ODE and said, X is my behavioral intention. I is a person, so I'm person I. There are J different things that I could do. For each of those things, I have a certain behavioral intention, and that intention is going to depend on my internal attitude toward taking that action, my perception of the social norm, and my perception of my behavioral control. The reason that we structured it in this form of having two additive functions and then a multiplicative one is that what this essentially gives us is that if you perceive your behavioral control to be zero, you're not motivated to take any action at all. And over here, we essentially have competition between your internal attitudes and the perceived social norm. So if you're, for example, your internal attitude is really negative, you think it would be really bad to put up a Harris-Walz sign, but all of your neighbors do it, and you want to be popular with the neighbors, that could lead to you doing the same thing, even though you were not convinced a priori that that was the good and right thing to do. So let's put some more math in here and some more collective dynamics and say, well, this is what happens within a person when that person decides whether to take action or not. And then at some point, that person is going to take an action, and other people are going to see that. So every person in my network or in my collective is going to see a bunch of actions over here. And those actions are going to lead to essentially some perceived social norm that we coined to be a nudge effect to take a certain action. Now, I just got the 10-minute warning sign, which means that I went way too much into detail with this. So I'm not going to talk much about the actual equation forms that we've chosen here. But basically, the diagram gives you the idea of how these collective dynamics should work. And when we run them in a simulation, what we find is, and so what we're going to see is the behavioral intention of an individual, the nudge effect that that individual sees, and we're going to see when and how many actions are going to be taken. Now, there's a continuous part of these dynamics. There's a discrete part of these dynamics, mainly that if you take an action, that is a discontinuous change in the system. And if you make some simple choices about what the functions are that I mentioned earlier, taking very simple ones that are just linear forms, then you still can create fairly interesting collective dynamics. And so what we have here is just a collective of 4 people. It's an all-to-all coupled graph, so everyone sees everyone. There's no preferences here. The rings around each of those nodes indicate their individual preferences. Red means you have a positive attitude towards taking an action. Gray means you have a negative attitude. The size of the ring tells you something about how strong your conviction is. So what we see is that if nobody really wants to take an action, then in most cases, nobody takes an action and that's it, just it. But if you have even just one player in your system who has a positive attitude, then depending on exactly how negative the attitudes are of the rest of the people in the game, and some playing around with initial conditions, you can either be in a scenario where your population is going to split into yaysayers and naysayers. So you have your one individual taking actions at some regular frequency, but in this other case, you see that this one individual is sufficient to gradually pull everybody else on the yaysayer side, and eventually you have this exponential growth of actions being taken within your collective. You can look at how the different aspects of internal attitudes, perceived social norm, and the like are affecting the system. One really interesting aspect here is that you have sometimes fairly long transient periods before you see those clusters or consensus emerging over time, which we thought was really interesting because that's essentially what we see in a lot of real-world cases as well, right? So you have like, are blockchain technologies, are NFTs, are those going to become a thing? Are those just a fad that is over? People have different opinions on that because there can be very long transients for technologies, for example, to be adopted or not. So we have that slow onset. Interestingly, in most social studies, you wouldn't be able to see people's actual behavioral intention. You would only be able to see whether people take actions or not. When you just have access to that information, it's really difficult, if not impossible, to tell what the asymptotic state of your system is going to be. And if we look at our model, we find a lot of parallels to the dynamics of leaky integrated fire systems, which might not be much of a coincidence, given that 2 people on our team had extensive experience with modeling neuronal systems. So one of the things that we see in our system that might, for example, be corrected by having more similarities, in fact, to a leaky integrated fire system is that we see when the system reaches consensus and everybody starts taking action, you have that cascade, like this explosive cascade of more actions being taken. These are log plots, so people start taking actions over and over again, and there's no dampening to that. So having some sort of refractory period might actually mitigate this effect. And so to conclude that second part, we wanted to give agents agency by incorporating the theory and planned behavior in collective modeling. For this to make sense, you essentially need to instill some form of agent heterogeny and temporality of shared information, so the information that I share with you. Its importance is going to decay over time. And we see some interesting effects, including long transients in the system. Now, how many minutes do I have?
Max of 5, but I think we should leave space for questions. So.
Oh,
yeah.
I see. So I'm already that much over time.
Well, I mean, you have 10 minutes after 12:20 for questions, but
okay.
however.
I'll go through this in 5 minutes. So this I wanted to bring up in part to address the young people in the room, where I see connections between collective dynamics and artificial intelligence now that I switched from studying collective dynamics to artificial intelligence. And I apologize to either who could probably talk about these slides much better than I can, but there's actually a lot of things that people who study collective dynamics and complex systems can bring to the table when it comes to studying artificial intelligence systems. I want to encourage people to see that value of what they can bring to the table, rather than feeling like, oh, I didn't do data science boot camp, so I'm of no value to the industry job market. So first of all, very clear connections that you have. Most of neural network learning is deep learning these days. You have network structures that have a mix of regularity and also some level of complexity in there. Thinking about how you want to characterize these network structures, especially if you apply some sort of sparsification to them, brings you back into the realm of network analysis, where I think people with insights into network analysis in other domains would have an interesting in-way to it. Using that bit of research that I explained a bit earlier, or something similar, you could think about predicting the correlation patterns that you're going to see at different layers within this network, or something where a connection strength change dynamically, for example, in transformers and the like. Here I have an example of graph neural network learning as well. So there's networks everywhere in here, and dynamics on these networks play a role. So I think there's a lot of interesting things that you can do here coming from a complex systems perspective. What I see now that I'm working in policy is that distributed computing is much of a bigger deal than I thought before, in part because in terms of training large neural networks, we have to deal a lot with privacy concerns. So it's not just that we want to see cloud computing and grid computing, it's that sometimes there is a need for thinking about federated learning setups where the training data isn't shared throughout the whole system, but there's some training happening locally so that privacy concerns can be met. And edge computing relates to that. If you have systems like that, or where you have a distributed computing infrastructure, sparsity and robustness, and therefore percolation theory, can play an important role in terms of deciding how you want to design your distributed system. There's a lot of temporality in how these nodes communicate, and so that, I think, leads to interesting problems on the complex systems front. And then perhaps finally, I want to briefly talk about agentic AI. So here the idea is you improve the outputs of, say, a large language model that you ask to do, for example, a programming task over here, by having another large language model do the bug checking, right? Sometimes when you try to prompt a large language model to give you code, there's going to be a bug in there. One way to fix it, if you don't want to do it yourself, is just tell ChatGPT, oh, there's a bug in here, can you please fix it? But the process of doing that iteratively is tedious, so why not have another large language model do that for you? And this is something that a lot of people on the industrial side are really excited about, specifically given that there seems to be a slowdown in the improvements of the large language models that don't implement agentic learning strategies, and there's some hope that agentic AI will help with that. And this essentially brings us into the realm of consensus finding and wisdom of crowds, right? If we imagine chaining up a lot of large language models to talk to each other, we can think about to what extent we want these agents to be homogeneous or heterogeneous, how complex we want them to be. Like if we chain up a lot of very stupid large language models, is that going to be better than having one really smart one? Where's going to be the kind of tipping point when you compare these two scenarios? And then for those people interested in governance, if we have a lot of them, like how should consensus finding in these groups work? Is it maybe there are some models, maybe you want to instill some sort of hierarchy or conditional contracts between these agents. And I think I'm going to stop here. There's a bunch of work on that already I'm going to briefly mention just this because it's really fun. So the founder of Bumble at some point said earlier this year that if you don't like how online dating works these days, fear not. In the future, all of us are going to have an AI concierge who's going to date other people's AI concierges before you even have to deal with any people. People have different feelings about that idea. However, if something like that were to come to pass, or we even want to consider that, it leads us to a scenario where we have social dynamics, where we have different populations, one of AI agents, one of humans that interact with one another. You can think of that living on a multi-layer network, and it has implications for AI futures and AI policy, as I can definitely attest. And there's some initial work on that from other colleagues in network science. And so with that, I'm going to come to an end, and thank you for your time.